This is my capstone presentation for the Masters in Science and Applied Data Science at Syracuse University. In this program at Syracuse University, students such as myself are provided an opportunity at the final term of the program to synthesize a presentation. This presentation consists of a collection of completed assignments and projects showcasing achieved learning objectives. I want to mention that the last project chosen in this portfolio was quite involved, so I will try to breeze quicker on the first project. The following list consists of learning objectives taken from the project portfolio milestone requirement for 2023. While I won't read each item in the slide, I will mention a few general notions. Prior to this program, I never used R programming, Shiny Dashboard for visualization, or performed much coding with Python data frames, which is an excellent way to organize data into tabular format consisting of rows and columns. I also never performed or used any NLP packages in any programming languages. Now that I'm at the end of this program, I want to briefly highlight later in the last slides. I am heavily involved in the area of data mining in the cloud. This is something I've never had an interest prior to this program. As we launch into the presentation, I want to list 3 different courses I've selected that best represent skills I've learned in the program. The first is Financial Analytics 654. This course taught in R with a focus of financial analysis using a framework called Shiny for visualization. I listed Python in the skills since I found a way to modularize Python code that could be invoked in R using a package called Reticulate. Next is Natural Language Processing 664. This course taught in Python and focused largely in NLP concepts. These include analyzing parts of speech, bag of words, and how to take documents of words and represent them in a numerical matrix in order to perform tasks such as classification or sentiment analysis. I added the MongoDB in the skills since I used a database for complicated operations of MapReduce to pre-process data on the final project. Lastly, Text Mining 736 was somewhat similar to IST 664, but expected stronger Python coding skills with a greater focus on how and what to do with text mining. Since this was my last project and course taken in the IST program, I attempted to create a much larger project involving a superset of skills from the overall program. We'll start with my first final project, Financial Analytics 654. This was one of my earlier projects in the program. In general, I tried to determine whether hacked or breached companies were bad investments in the medium term. I was able to recycle code from previous assignments to perform analysis as well as visualization using a Shiny Dashboard in the web browser. The requirements were pretty straightforward, that is to use R and visualize using Shiny Dashboard of our analysis. I generated a data set consisting of company tickers that have been hacked or breached and merged them against stock market data using the Quandl API. In hindsight, I wish I used something like Yahoo Finance, since Quandl was quite limited and generally didn't have prices, instead only volumes. Nonetheless, I was still able to perform some R coding using Shiny for the dashboarding. On the left, I was able to show the variance of volume between tickers selected in our dataset. In general, volume is a measure of risk and can help indicate whether strong or weak buying pressures for a given stock ticker was present. We see despite Facebook hack, the high variance we see indicates investors still perceived an opportunity to profit through consistent buying and selling. Sometimes well-established companies are resilient in the medium to long term and often fall back to the overall company fundamentals or market technicals. On the right, a Markowitz model was generated using code recycled from an earlier assignment in the class. The tangent line, or known as the efficient frontier on the curve, indicates the most optimal distribution within the given investment portfolio. It would have been interesting to make a slider or input box in the shiny dashboard. This way, users could change the weight or time scale, causing the efficient frontier to update in place. Similarly, mixing and matching normal tickers against our dataset may have been more interesting. Finally, time series prediction and forecasting was performed. While the course heavily focused using R, I wrote and modularized Python code to be invoked through R and visualized in the same shiny dashboard. In general, I found the ARIMA model was faster and more accurate. This could be because the neural network generally requires more data to allow splitting the data set into train, test, and validation. In layman terms, neural network reads the same data set many more times than a traditional statistical approach such as ARIMA. This requires a portion of the original data set to be removed from the training set to later be used for prediction validation between each data pass. Ultimately, this allows the neural network to learn to tweak the model it's generating. However, this reduces the overall training dataset to learn from. ARIMA, on the other hand, doesn't have this forward and backward propagation, and thus able to use all the designated training data for learning on a single pass. The second project in my portfolio, I had a larger ambition of producing a chatbot using materials covered in the short 10-week course. Like the previous project, the final project topic started formalizing around weeks 6 through 7, leaving around 3 to 4 weeks to complete the overall final project. In order to complete the task, the goal of creating a chatbot needed to be broken up into several problems, with a possibility of the first being sufficient fallback to turn in for the overall project. In general, the desired goal consists of 2 or more classifiers guiding an input sentence to a neural network-based chatbot. Firstly, a classifier is trained to detect whether an input is a valid question. If the input was detected as a valid question, the next classifier determines what specialized chatbot to engage. What was desired versus what was obtained was largely a factor of sheer engineering hours needed to investigate various datasets, performing base requirements, satisfying the project, followed by attempting to learn the MongoDB MapReduce, as well as the NMT neural network framework, both of which weren't directly covered in the course, and was something that was investigated in addition while creating the final project. Originally, I discovered the entire Reddit data first half for 2016 could be downloaded. I intended to use the dataset for all classifiers and chatbot in the project. My partner discovered the Reddit data wasn't tagged and could not be used to train classifiers. Luckily, I found a Stack Overflow dataset labeled by channels. At this point, we were a bit overwhelmed with the project deadline. My partner and I agreed he was going to train a classifier on predicting channel categories, including some exploratory data analysis on the Stack Overflow dataset. Myself, on the other hand, focused much less on exploratory data analysis and trained a question classifier on a third dataset I discovered from Carnegie Mellon. The idea was that I was going to expand the base minimum requirement my partner was constructing. If my classifier detected a question, it would initiate my partner's classifier to suggest a channel topic from Stack Overflow. Since my part was relatively simple compared to his, I expanded my efforts storing the Reddit data into MongoDB in order to perform transformation on the data using a framework called MapReduce. Ultimately, the transformed data would be a sequence of statement response pairs needed to train the chatbot. Using a Jupyter notebook and pre-processing data using standard NLP tokenization techniques, I was able to train a classifier to predict whether a sentence was a question. For such a simple task, I actually expected results to be slightly better than received. Nonetheless, a 72% accuracy was achieved, and the corresponding random forest model was pickled. This is similar to creating a zipped file of a directory containing files representing the trained model. At the end of this project, when I created an interface between the various models trained by myself and my partner, it was essentially unpickling the given models, which is equivalent to unzipping a tarball so it can be executable in Python. My partner trained a single multi-class classifier to predict a label from a supplied sentence. However, the data used to train his model was quite unbalanced. We see a significant majority of content was related to math questions. From the confusion matrix, a sentence related to Unix could almost equally be predicted incorrectly as the super user label. I think an improved approach for above is to potentially train two models. The first is simply a classifier to predict either math or not math, while a second classifier is trained as a multi-class classifier trained to predict remaining labels, not math. Essentially, the non-math class would be trained with all and only non-math labeled data. If the math classifier predicted math above a threshold, say 85%, then we could conclude the sentence is math related. However, if math is not detected with the math classifier, then a second multi-class classifier could be invoked to predict if the sentence is any of the remaining class. At this point, the highest prediction score between the two classes could be chosen as the final result. This approach could easily bring this task above 85% accuracy. In the last component of this project, I had to learn during my own time outside of taking the course and performing the final project how to use MongoDB database, as well as its MapReduce functionality. Essentially, the Reddit data needed to be pre-processed and broken into a series of question-response pairs through an extract, transform, load-like process for unstructured data. Basically, each post having some ID could have any number of response with a matching parent ID. Each of these ID and parent ID pairs would be grouped through the MapReduce process. Once the data was transformed and inserted into the Mongo database, we were able to train a neural network model using many of these post-response pairing. We use neural network framework called NMT, which is well known for language-to-language translation. For example, converting English sentences to French. I use this framework instead to build a chatbot in the same English language. I had maybe 1 week to learn and try to investigate this new NMT neural network framework with the MapReduce dataset I created. I never got enough time to check under the hood of the NMT framework to understand the confidence scores could be customized. In truth, we had enough data for a working chatbot, but I wanted to show on the left side of this slide a workflow where the chatbot could not return a sufficient response. For example, responses with poor quality confidence scores. For this example, I said if NMT returned a blue score less than 12, the chatbot response would be suppressed. Then my team member's classifier would be initiated. However, as mentioned earlier, the label classifier was quite imbalanced. When a generally vague sentence is supplied, the return result can easily be labeled math. Finally, the last project in my capstone portfolio is IST 736. This course was focused on two general aspects: data mining as well as machine learning based on text obtained from data mining. Being the last course in the program, I wanted it to be a little more special and representative of previous courses I've taken in the overall program. This topic was chosen to determine whether stock market sentiment could predict aspects of the stock market. Like IST 664, fundamental concepts such as exploratory analysis for NLP were conducted, as well as we'll see in the next slides, which this time served more on a practical sense, determining what subtopics to target and try to analyze. Unlike the previous two courses, this course provided better guidance on how to obtain data through various APIs rather than hoping relevant data sets were available for download online. Before jumping into further slides, I want to generally present how the project was organized on a high level. First, I developed Python code to extract tweets from various financial analysts using Twitter API. Using this data, I performed exploratory data analysis using LDA, or a natural language processing technique that groups similar words together. Once I had a collection of groups of words, I was able to determine which stock ticker were generally trending for a given financial analyst. Refining code from Financial Analytics 654, I was able to obtain ticker data based on what was trending. Next, I converted tweets for each financial analyst to numerical sentiment scores for each positive, negative, and neutral sentiment. Borrowing a Granger financial hypothesis test, I tried to determine whether one time series could predict another time series, namely whether any of the sentiment time series could predict ticker time series. Additionally, I was able to vectorize all tweets for a given analyst into a distribution of word occurrences, a weighting of how many times a word has occurred in all tweets for a given financial analyst. I trained this vectorized data using a classifier against two labels, momentum up and momentum down. These momentum values were generated using a custom signal analysis stepwise equation I created. Basically, if a lag ticker value exceeded, for example, one standard deviation over the trend line, it received a value of 1, or 2 if it was 2 standard deviations above the trend line. The inverse was similarly defined. This essentially provided me a standard gauge to determine whether tweets from a financial analyst could predict the momentum of a ticker value. So the takeaway approach is twofold. First, determine whether Granger causality test could indicate whether analyst sentiment could predict ticker time series selected from the exploratory analysis. And second, if yes, use the classifier trained for the given financial analyst to predict whether future ticker price will be bullish, bearish, or very bearish. Based on what was discussed, I chose to track 5 financial analysts using the Twitter API. At the time when I wrote code, I could only query the most recent 3,200 tweets for a given Twitter handle. I believe this is the same limitation today. I stored these tweets as flat files on my local system. No databases were involved. My Python script also queried the Quandl API, which was a much larger time series scale, So joining the two didn't really cause much loss in Twitter data. It actually, I don't think we lost any data. As mentioned earlier, I wish that I had used Yahoo Finance API, since it provides more data including company ticker values rather than just short or total volume. I performed topic modeling using an algorithm called LDA and configured the algorithm to return 10 topics for each financial analyst. Since I performed 10 topics for each analyst, this means I generated 50 total topics. In this slide, I chose to show 2 word clouds out of the 50 generated to give a visual sense of how LDA works. From here, we can easily see what general things a financial analyst discusses in the course of 3,200 recent tweets. In the case of the stalwart, I may choose to obtain and analyze Apple, Tesla, or Netflix ticker data. On the other hand, for Liz Ann Saunders, I may choose some oil company, maybe Exxon or Chevron or Metallica Metals Corp. However, if I think the word oil is too vague, then I should have 9 other topics to review and consider for Liz Ann Saunders. Using LDA topics, I performed due diligence and attempted sentiment analysis of each topic. Not shown in this slide, I also performed, as mentioned earlier, the same sentiment analysis of each tweet for a financial analyst as a function of tweets in sequential date-time order. This provided me time series dataset for each sentiment, positive, negative, and neutral for the most recent 3,200 tweets on a given financial analyst. Having sentiment time series and ticker data determined by LDA topic modeling and downloaded through the Quandl API, I was able to perform another brute force, shotgun-like analysis. Namely, I performed Granger causality hypothesis testing between the VIX and Liz Ann Saunders, 3 sentiments as a baseline measure. Next, I performed the same hypothesis testing between every time series combination of each 5 financial analysts against roughly 12 different ticker symbols to see if results were better than the baseline. Generally, with hypothesis testing, we want a score of less than 0.05 relevance. Similar to previous slides, I'm only showing 2 results of many. This is just to give a representative idea of what some or most results look like. As we can see, we have some good results, where the relevance value using k-fold-like analysis generated scores much less than the 0.05 threshold. With these results, a general consensus could be said that S. Joseph Burns' positive sentiment Granger causes Amazon's volume at a 0.05 significance level. Since we were able to determine via the Granger test that S. Joseph Burns' positive sentiment could forecast ticker momentum, we could proceed to the second case. That is, train a classifier to determine whether tweets could predict whether ticker value or volume would increase or decrease based on the customized stepwise equation we developed. Ultimately, I was able to train a Bernoulli naive Bayes classifier, which was roughly 94% accurate in predicting whether a tweet could forecast increase or decrease in stock volume. Again, the analysis was performed for each of the 5 analysts for a range of tickers defined by the topic modeling for each of the 3 sentiments. But I've only showed one result to give a representative idea of the analysis that was performed. And to reiterate, at this point, we've proved using the tools and methods we've selected 2 points. First, Granger financial hypothesis test was able to conclude that positive sentiment from S. Joseph Burns could forecast Amazon ticker volume price. Second, general tweets from S. Joseph Burns could forecast future momentum of Amazon ticker volume. For example, are investors going to be buying and selling a high volume or very high volume? These could serve as indicators of risk and opportunity for gains to be made. Before closing out, I want to mention that I didn't arbitrarily select the Bernoulli naive Bayes for a classifier because it sounds fancy. I actually ran a series of benchmarking to determine out of a selection of different classification models which would perform best on the S. Joseph Burns dataset. Then I ran a k-fold analysis, which basically runs the same model 5 times against the same dataset with different sampling to see if the model performance is consistent. Overall, the Bernoulli naive Bayes generally performed best. And I want to apologize again. While the slides show model comparisons for S. Joseph Burns, I want to stress that I perform this type of benchmarking for every combination of financial analysts. This basically concludes my presentation, but I want to address one final question: why I haven't submitted my portfolio since I've completed all requirements since 2019. The answer to that is largely because I had no requirements at my profession that needed this degree immediately. Further, I was more focused on expanding the previous 3 projects shown in this portfolio, but more in the context of big data application in the cloud. I was more engaged learning how to do cloud and how to do big data, and this consumed me more than wanting to officially graduate. So here's an architectural diagram which has been running for the last 2.5 years nonstop. It's actually only a small set of what I have already built in AWS. Several of the pain points with the project-based courses in the Syracuse program were data related. So that was in part of the motivation of the cloud system I have built and running today. It consists of my own API that collects stock market data every minute for roughly 200 stock ticker symbols every day between opening of stock market 9:30 a.m. to close 4 p.m. They get dropped into a stream, and several processes organize this stream into a data lake partitioned by sector, industry, year, month, and obviously the ticker symbol itself. The data lake allows me to perform big data like analysis using Spark or Hadoop, as well as machine learning and neural network training we saw earlier. This spring, I spent time building a front-end website that displays some metrics for this data lake architecture. For example, stock splits can happen any day of the week. When this occurs, the given ticker price could change, maybe 4 to 1. This means all data points collected in the data lake are no longer valid. For example, Tesla could be worth $400 yesterday for 1 share, and today it could split into 4 shares at $100. So I had to create an automated system that checks every morning between 12 a.m. and 1 a.m. for stock split happening that morning. If a ticker that my system is tracking is found to have a stock split, the automated system will backfill and correct the stock ticker price. We can see in the screenshot here The stock split was actually performed on the Tesla ticker and took roughly 1.5 minutes to complete. There are some additional features of the system that are nearly complete and in the works, but I will conclude here. The purpose of the last two slides was really to show that while I have officially concluded my time within the Syracuse program, my learning and application of data science, whether as a hobby or practitioner, will continue on regardless. Thank you.